Good morning, my name is Moritz Rietschel. I'm at the architecture faculty at UC Berkeley, and today I'm going to present our paper titled Mediating Modes of Thought, Large Language Models for Design Scripting. So I want to start out with this video that shows our prototype system. We take something like a quick sketch of, in this case, a suspension bridge. And it doesn't have to be very detailed. You can just say, this is my simple suspension bridge. I want a catenary curve right here, and then I take that image and hand it to our system in Grasshopper, and then that gets translated and with like vision language models that sort of analyze that sketch, see what they have, and then create a Grasshopper model from it. So we get a parametric model of like some suspension bridge. It's not exactly what we sketched, but it's sort of like it's getting there. And of course, that's a Grasshopper model, so you can change it to whatever you want it to be. We theorized these two modes of thinking, which is the designer that sort of tries out and by trying out finds their design through testing and adapting, and it's a highly dynamic process. And then the computational tools that often require you to make all these choices up front, and then only then can you like start authoring your algorithm, right? So you got to decide exactly what are my inputs, what are my operations, and then you start modeling your bridge, for example. So in an extreme form, we can compare sketching with pen and paper and authoring Grasshopper definitions. While the former is inherently iterative, where you find the correct line through layering and trying out, Grasshopper definitions require you to precisely define what are your input parameters, what are the operations, and you only get a sort of visual feedback once the algorithm, or at least part of it, is complete. You cannot sketch a Grasshopper definition. So we set out to make these computational tools accessible earlier in the design process and make them more fun. So, two modes of thought. We approach solution through sketching and we navigate constraints along the way, or we sort of decide everything up front. The designers, they draw from their experience to make these judgments along the way, and their design is kind of tacit. But computational tools are definitely empowering, but they still sort of, if you're not a programmer architect, they're very hard to use. So for most architects out there, things like Grasshopper are actually sort of have a huge barrier of entry. And you end up sort of orchestrating the relationships and operations in your 3D model much more than like designing in the traditional sense. So enter machine learning models. So for example, a image diffusion model slowly denoises step by step and finds the design that it's creating. So it's kind of like a sketch where through its experience, it sort of triangulates for a new context from what it's seen before and discovers its design in this like iterative process. These models have learned from experience, much like their human counterparts. They're sort of strange blobs, I think. You can poke them and kind of try to get them to draw what you want, but sometimes they'll do it, sometimes they won't really match your expectations, and then you just go back to the text input and you sort of like tweaked it to get it a little bit closer to what you were going for. Other approaches in 3D model generation also use a similar approach where they have diffusion models that generate meshes, for example, that sort of kind of get to what you wanted and are approximations of sort of a geometry that you were looking for. We instead use large language models. They have a really good learned understanding of our human world, which lets them sort of infer your design intent. And they have internal representations of geometries and objects and so on. So if I tell a large language model, oh, an umbrella, it can sort of infer what that shape would look like. Not look like, but what it's made up of. The large language models combines this with great coding capabilities. So it's actually really good at programming. It excels at writing algorithms. It has great performance on like math and physics problems. And that makes it sort of between these two worlds, right? It's this strange blob that can sort of do one thing, can sort of do the other thing. And we propose that combining the sketch-like approximations of machine learning with deterministic structures of computational design, and in our case, Grasshopper, can actually create a more powerful and useful tool than purely the output of a machine learning model. So we combine this large language model with Grasshopper scripting to sort of pour its imprecisions into a more precise format, right? And then that allows us to sort of leverage both of these two. And that's why we call it the mediator, right? We're mediating these two modes of thought. So what did we actually do? This is sort of what our system looks like. From a text input and later, since we wrote this paper, actually also image inputs, we have a model to sort of think about what is the representation of this query. So for an umbrella, that would be, oh, an umbrella in a CAD environment, that might be a cylinder and maybe a canopy and so on. And then we ask it to define the relevant inputs. So we have maybe the diameter of the cylinder, we have the height of the umbrella, we have the diameter of the canopy, and then we have these inputs and the final geometry, and then we ask it to step-by-step iterate through these operations that lead from these inputs to that final geometry. So in this case, that might be the diameter value input goes into a circle component, then we extrude that circle component, then we sort of loft the canopy and so on. The result is AI-generated 3D model in a way, but from an interaction point of view, it actually exposing this grasshopper script logic really centers the designer and their agency instead of just providing you like some mesh model. Because you can go back in, you can edit, you can append it, you can collage together different grasshopper scripts. You can combine them however you want. You can go back into that logic that was created by the language model and you can change it, right? You're not just given this like final output. Instead of going back to the text input and poking this LLM slightly differently, give it a little different query or something like that to try and get a different geometry, you can actually interfere with the geometric logic wherever you want, at the start, at the end, wherever you want. And you also, the sort of logical flow of Grasshopper gives you an immediate grasp on the logic that's happening. So it's a lot more informative than just getting some model when you actually know where that kind of came from and sort of what the assembly logic of it is. Of course, the 3D models generated in this way are in a way also precise, right? You can give a precise diameter to the cylinder. It's not a diffusion model that approximates a mesh, but this is actual CAD that you can use with real world diameters, values, sorry. Okay, so the final geometry is actually the result of the deterministic grasshopper environment, right? So you're back in your CAD that you actually know, but the way that you arrive there is through a language model. So now I want to go on to how we've expanded the system since writing the paper. So for example, here I grab a graphic of the Shanghai Tower of Google Images, which includes a schematic and a plan view. And then I have a vision language model look at that and create a very detailed description of it. And then I can hand that detailed description to my system, and I actually get a functioning twisted tower grasshopper script from it that is obviously fully parametric, gives me a lot of sort of intervention, opportunities for intervention, and a good starting point if I want to make my own twisting tower. It's interesting, you can see it actually generated this central concrete core cylinder, then this twisting and tapering geometry, and then the lines on the outside are steel columns that it saw in that schematic that it also tried to add into that geometry. So to achieve this kind of result, the model must use more than just the image that I provided, right? It falls back on these learned representations like some designer might. It opens up space for imprecisions and deviations from my actual intent because it takes that image and it sort of infers a lot of things that to arrive at this model. But that also refers to a kind of problem solving and creativity within the model. It's what discerns a good helper from a lazy one. It's able to execute without perfect instructions, right? I will give him an image and it will sort of infer all the things that it's not provided with yet. So to sum up our contributions, we situate machine learning models as mediators between designers and computational design tools. We parse imprecise model output to these node operations and a deterministic logic, which also handles the tendency for imprecision of the model. We produce editable parametric logic instead of a final model to give the user maximal agency to edit and append and work with the result. This is by any measure still very early work, and these language models are actually becoming more ubiquitous and effective in the coming years, as you all know. So I want to end by posing to all of you the question, how does CAD and design practice change when large language models understand design intent and at least they can infer it, infer it to some level, and then you can employ them to actually construct computational logic for you. Thank you. That was Mediating Modes of Thought. This is work I did with Fang and Steinfeld. Thank you, everyone.